All right, so very good evening, guys. Very good evening, guys. Yes. The session started. We'll just check the audio once. Very good. Noted. So, although we had planned this session a little earlier for today, but it got stretched to 7:40 and now 8 p.m. We'll keep it short. We will keep it short. We will see how do we take the maximum advantage. But yes, we'll be needing one more session for chemical kinetics. Without wasting any more time, I'll quickly give you an introduction today to what is kinetics, what is the rate of the reaction, a little glimpse of what is called as rate law. Right? So let us quickly start with it. We're talking about the chapter which is called as chemical kinetics. Right? And in one of the shorts that we had prepared for YouTube, you all know that kinetics involves or talks about the rate of the reaction. The rate of the reaction, which means in this specific topic, we talk about how fast the reaction goes. How fast the reaction goes. It talks about how fast the reaction goes. And when we say how fast, we always talk about something which is concentration. How fast the reactant is consumed. The reactant is consumed, or how fast the product is formed. It should be how and not for. How far and how fast the product is formed or produced. Right, sir? Right? Very simple, sir. Any reaction will have two components, reactants and products. Reactants are something that gets consumed. Products are something that gets produced. Right? Products are formed. Reactants are consumed, utilized. Right, sir? So say for example, in the reaction A giving B, A is the reactant. Wow, what a simple knowledge. And B is the product. So A is something whose concentration decreases with time. Very important. Whose concentration decreases with time. Very important. For reactant, my concentration is decreasing with time. And parallelly, for product, my concentration increases with time. Implies when I say reactant, I always say final is less than, final concentration is less than initial concentration. Final concentration is less than. This is the key statement for reactants, right? This is the key statement for reactants. However, for products, my final concentration is greater than the initial concentration. Why I am telling you this? Because this is a lot of significance in using plus minus sign in just 5 minutes from now. Because the product concentration increases with time, the reactant concentration decreases with time. So that plus minus really plays an important role. Very important. All right, final greater than initial, final less than initial. So just as a general convention, I should say conventionally, we will talk about reaction as we will talk about reaction as R giving P. Short form, reactant giving product. Alright, reactant giving product is my symbolic methodology to show that. Right, sir? Now, so basically this chapter talks about the rate of the reaction. So chemical kinetics talks about the rate of the reaction. Rate of the reaction. Whose definition? Now we almost know that it is defined as the change of concentration as the change of concentration with change in time. With change in time. How the concentration changes with time is called as the rate of the reaction. Right? What is the speed of the vehicle? What is the speed of my car? So total the distance traveled in a given time. That way. This is how you calculate speed, total distance upon total time. So same is that rate. Change in concentration upon total time. That is how we do it. Chemical kinetics rate is gonna be change in concentration upon change in time. Right? So basically, my rate of the reaction will be change in concentration upon change in time. That is delta R upon delta R upon delta T. Concentration change upon time change total. Right? Concentration change upon time change. Now understand one thing very, 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 very clearly, guys. What happens is, in physics also we do that way. Rate is of two types. Rate of reaction is of two types. Number one, it is called as average rate, and number two, it is called as instantaneous. Instantaneous rate. One is called as average rate, the other one is called as instantaneous rate. Right? One is called as average rate, the other one is called as instantaneous rate. Now, when we say average rate, we want to say it is change in concentration over a period of time. Over a period of time, which means it is talking about delta A or say delta R upon delta T. It's an average rate. Average rate of the reaction. Delta R upon delta T. Instantaneous rate is change in concentration at any specific time interval. At any specific time interval where delta t tends to 0. Instantaneous velocity, instantaneous acceleration. That is something called as instantaneous. So what is that? Change in concentration at any time interval, where delta t tends to 0 implies my rate will be minus, not, I'll not put minus for now. I'll simply put rate equals dr by dt. Instantaneous state differentiation dr by dt. Right? dr by dt. Sorted, sir? dr by dt. Now comes the main concept that we discuss about here. It is, it is what, sir? It is that for reactants, comma, final concentration is less than initial concentration, right? Therefore, delta R is negative because delta R is final minus initial. Change is what? Final minus initial. Therefore, to make the rate positive, to make the overall rate positive, to make the overall rate positive, comma, we add an additional negative sign. Additional negative sign implies in terms of reactance, comma, it is gonna be minus dr by dt or minus delta r by delta t. Minus delta r by delta t. This is how it is defined as minus delta r by delta t. Sorted, sir? So say for a reaction example N2 plus 3H2 in equilibrium not with 2NH3, my rate of the reaction expression is given by rate of the reaction is given by minus dN2 by dt because reactant, so minus charge, minus 1 by 3 dH2 by dt minus because reactant and 1 by 3 because for every 1 mole we are comparing equals to plus 1 by 2 dNH3 by dt. This is how you write the overall rate of the reaction. Important, right? Sorted, sir? But then here we see that rate of the reaction, that rate of the reaction depends on the concentration of the reactants, concentration of the reactants and concentration of the reactants and what? Concentration of the reactants and what? Order. Now this is something which is going to be discussed now. Right, sir? Order of the reaction. Now what is that, is sir? That rate, I should not be saying that. What we should say is that for a reaction is 2A plus 3B in equal to say 3C. Okay, example. This is an example that we're talking about. 2A plus 3B gives you 3C. Here, sir, my first of all point number one, rate depends only on the reactant concentration and not products. Only on the reactant concentration and not products, right? For example, rate is proportional to a to the power x and b to the power 5. In short, no dependency on c. No dependency on c. No dependency on c. A to the power x and b to the power 5. Two most important things that we take up right away. So when first of all, this is called as rate law expression. This is called as rate law expression. In short, rate is proportional to a to the power x, b to the power y, and then when we remove this proportionality sign, rate is equal to k, a to the power x and b to the power y. A to the power x and b to the power y, where k is called as rate constant. Very, very, very important. K is called as rate constant. X is called as order with respect to A, and Y is called as order with respect to B. We add these two, x plus y is called as order of the reaction. We call as the order of the reaction. We call as order of the reaction. Anjali, good evening, in case you're still on the chat, and Vijay also, good evening. Right? Rate constant. Although I think you've done a little late, rather I'll just keep it for another 10 minutes or so. I'll just keep it to order only for today, and molecularity and then what is first order, second order, those things I will discuss in the class tomorrow, and we'll complete it. Right? We'll complete this chapter in total tomorrow. Total, it will be completed. Right? Rate constant expressed is called as the order of the reaction. Now, quickly we tell you here k a to the power x and b to the power y. Now, x and y, they are experimental quantities. They are experimental quantities. X and y are experimental quantities. May not be equal. May not be equal to the stoichiometric coefficient. To the stoichiometric coefficient. May not be equal to the stoichiometric coefficient. Right? May not be equal to the stoichiometric coefficient. Ishrat says, nice explanation. Ishrat, thank you so much for it. But I hope it is clear to you also. Thank you for it. But experimental quantities may not be equal to stoichiometric coefficient. Remember, guys, why this is a little important is kinetics comes to class 12th. And just before this chapter in class 11th, we have done something which is called as equilibrium constant. I'm just breaking that scenario for now. Say, for example, the reaction is 2A plus 3B in equilibrium with 2C plus 4D. It was very clear that my capital Kc, which is equilibrium constant, is given by d to the power 4 c to the power 2 divided by a to the power 2 and b to the power 3. In short, the concentrations are loaded to their equilibrium, to their stoichiometric coefficients. This is something which needs special attention. That is, in equilibrium, my powers are equal to stoichiometric coefficients. No doubt in that. However, in kinetics, it is not sure. Indeed, the powers could be x and y, x comma y. They could be positive, negative, fraction, as well as 0. It could have any value. It is only experiment driven. It can be calculated only by experiments. Right? How that was not the case in case of chemical equilibrium. Very, very important. In equilibrium, it is always to the power. So, sir, now what I want to tell you here is that, say, for example, if my reaction is, say, 2A plus 3B giving product, so what you have to write is rate is proportional to A to the power x and B to the power y, and rate is equal to k A to the power x and B to the power y. Right? This is called as rate law expression. Already we have mentioned above, this is called as rate law expression. So now what is order, we should say? Order will be defined as, so now what is the order that we define as? Order is defined as the powers, is defined as the power to which the stoichiometric terms are raised, to which the stoichiometric terms are raised, to which the stoichiometric terms are raised in the rate law expression. In the rate law expression. Very, very important. What will be my impact on the rate of the reaction is called as the order of the reaction. Here, let me tell you one thing, guys. Let me tell you one thing, guys. We have two orders in syllabus. Zero order means no impact of concentration change, no impact of concentration change on the overall rate of the reaction, on the overall rate of the reaction. No impact of the concentration change on the overall rate of the reaction. No impact. Not at all any impact. No impact of change. Right? However, this is zero order per se. However, when we say the first order, so rate changes in proportion to rate of the reaction changes in proportion to rate of the reaction changes in proportion to the change in concentration. I'll show you this by an example also, but that is how we do it. It is proportional to the change in concentration. I'll give you the examples right away here, but that is how we do it. The next step that is most important, very, very important rather, is called as unit of rate constant, which is called as capital, which is called as small k, unit of rate constant. How do we do it? So the case was that rate of the reaction is equal to k, a to the power x and b to the power y. Correct? Or say the order of the reaction is x plus y. So what do we say is that for an nth order reaction, nth order reaction, here the order is x plus y. So for an nth order reaction, comma, the unit of k is actually mole to the power 1 minus n, liter to the power n minus 1, second to the power minus 1. This will give you 4 marks in the NEET exam. Mole to the power 1 minus n, L to the power s minus 1, s minus 1. So for example, if I'm talking about the first order reaction, it's gonna be mole to the power 0, liter to the power 0, s minus 1, which implies the overall unit is minus 1. First order reaction, s to the power minus 1. Second order reaction, what will be the value? Sir, mole minus 1, L1, S minus 1. So answer will be mole minus 1, L minus 1, liter minus 1, liter 1, not minus 1, liter is 1, and then S minus 1. And how this has been calculated is also really important to understand. How it is calculated, sir? Remember, rate is change in concentration upon change in time, right? So rate's unit of rate is what? It's mole per liter because it is concentration, mole per liter per second because upon time. This is your, what is this? This is your rate. And then A or concentration is anyways what is mole per liter. So that is how it has come from, because rates unit is also constant, which is mole per liter concentration upon second inverse, which is time. Right? Finds a unit of rate constant, mole 1 minus L, mole 1 minus N, Ln minus 1, and that is your, what would I say, S minus 1. Really important concept, tends to give you 4 marks in a single NEET question. Alright. Now quickly I will give you an example to close this call for now. It is that, sir, my reactant is giving product and I am talking about a zero order reaction. So how do I do it is really important. Zero order reaction. How do I do it? Remember guys, it's gonna be minus dr by dt is equal to k, minus dr by dt is equal to k, or is equal to k r to the power 0. And why r to the power 0? Because r is the reactant and to the power of it, power is the order. So when I'm talking about the zero order, it by default signifies that we're talking about to the power 0. Means I'm talking about minus dr by dt is equal to k. Anything to the power 0 is 1. Quickly, sir, minus dr is k dt. Okay. Sir, dr is minus k dt minus k dt integration. Right, sir? So what I have is r is equal to minus kt plus c, where c is called as constant of integration. Quickly, at time t equals to 0, at time t equals to 0, comma, rate or say concentration is equal to R naught. R naught is the initial concentration. So means what? R naught is equal to minus K0 plus C implies C is equal to R naught. We put this value here, we get K is equal to R naught minus R by T. And this is how your result 1 is published for a rate constant for a zero order reaction. For a zero order reaction. Anjali says zero order reaction time is 0. No, Anjali. Reaction will go on. Time is not 0, Baba. Where is time? No. At time 0 means initial concentration. When I say time t equals to 0, I want to say at beginning of reaction. So when I say at time t0, it is the beginning of the reaction. At time t equals to 0, we talk about beginning of the reaction. So K is equal to R naught minus R upon time is my rate constant of the zero order reaction. And I'm not naming the quantity for now, but if I tell you that at 50% concentration means T half, we will talk about this in the next session, half life, we say T half is R naught minus R naught by 2 divided by K. R is equal to R naught by 2. R is equal to R naught by 2. That is, my concentration becomes half. Concentration becomes half of its original concentration. So, and the answer that I get here is R naught by 2K. Most important stuff. Most important thing. Most important. R naught by 2K. Where again, R naught is my initial concentration. Quickly pen it down. Quickly pen it down. Quick. Quick pen it down. Copied? Chalo. Copied? So if it is copied, guys, this is good. And this is how you define as the rate of the zero order reaction. Rate constant of the zero order reaction. Quickly, I tell you this equation again, which was Kt, which was K is equal to R naught minus R by T, which is Kt is equal to R naught minus R. Comparing it with y is equal to mx plus c. comparing it with y equals to mx plus c, a form of mathematical straight line, I should say. Then how do we plot it out, sir? My r is equal to minus kt plus r naught. This is gonna be my y, which is concentration here, concentration on the y-axis, time on the x-axis, concentration on the y-axis, time on the x-axis. My slope of the line is minus k. R naught it starts with and then it gradually decreases with the slope of minus k. With the slope of minus k. Very, very important for a zero order reaction. Slope of the curve is negative of the rate constant. Very, 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 very important for a zero order reaction. For a zero order reaction, comma, for a zero order reaction, comma, slope of the curve, slope of the concentration versus time curve is negative of the rate constant. Very, very important. Very, very important. Copy it down. Only this is the fact that remains to be penned down for zero order. We sum up the class here for today. I'm so sorry, it's just 40 minutes for now. But we will continue kinetics in a little longer session, probably tomorrow, so that we are through it. Right? A little more commitment for today. But then yes, we'll continue with kinetics tomorrow and we would summarize it immediate basis. All right, fine, guys. So thank you so much, Anjali, for your doubt as well as your comment here. Thank you, Ishrat and Vijay for joining the class as well. Take care, guys. Have a very, very sweet night. Already 9 p.m. on the clock, 8:48, and we'll have more sessions like this for all the chapters of chemistry. All right, fine. Take care and God bless you. Bye bye. Good night.